Here's the next question, question number 40. A three-phase cable is supplying 800 kilowatts and 600 kVAR to an inductive load. It is intended to supply an additional resistive load of 100 kilowatts through the same cable without increasing the heat dissipated in the cable by providing a three-phase bank of capacitors connected in star across the load. Given the line voltage is 3.3 kV, 50 Hz, the capacitance per phase of the bank expressed in microfarads is dash. Okay, so this question is not a multiple choice, so we will have to solve it step by step and see what we get. Okay, so we have been given that the three-phase cable is supplying 800 kilowatts of reactive power and 600 kVAR 800 kilowatts of active power and 600 kVAR of reactive power. Okay, so I have mentioned this because we will have to find out what kVA value is for the three-phase cable given to us. Okay, now the capacitance per phase, remember now here the units are very important. We have to be very careful. Capacitance per phase has been asked, so that's C is equal to 1 by 2 pi f x c. That is our formula. This formula should pop into your head as soon as you find the question saying capacitance per phase of the bank. So here we have the frequency value given to us, but we have not been given the value of the reactance, the capacitive reactance xc. So we will have to find this value first. Okay, so coming to the first statement in the question, three-phase cable supplies this. So the first step, find out the kVA value. The kVA value is the resultant of both active power and the reactive power. Now you are quite familiar with how to calculate the resultant power, right? So the resultant power usually is, we use the Pythagoras theorem as such. So here is the calculation. kVA is the resultant of kW square plus kVAR square taken under root and solved to get 1000 kVA. So this is the value. You can work it out and check. So the next step, once we find out what the kVA is, we need to see the next statement here, which says that additional resistive load is given for 100 kilowatt. So for an additional load of 100 kilowatt, so the total active power is 800 plus 100, which becomes 900. And it is also said that the heat dissipated in the cable is not considered. Over here it said without increasing the heat dissipated. This should tell you that the current is constant. The current should be constant. Now, if the current is constant, that also tells us that kVA is constant. So throughout this first part of the problem, our value of 1000 will not change. So that is our next point here. Current is constant. When the current is constant, kVA rating is also to be constant. Now, the next thing, as I mentioned here, an additional resistive load of 100 kilowatt is provided. So which means that's 800 plus 100 to give us the active power of 900 kilowatts. Now that we have the active power, it is necessary for us to find out the reactive power as well. The reactive power in terms of kVAR. So the reactive power can be found by using the same formula here, just rearranging it. kVAR would be root of kVA square minus kW square. So we have the value of kVA as 1000 and the kilowatt is now the new value 900. Now we substitute both of them and find the value of the reactive power to be Q is equal to 435.889 kVAR. You can check this as well. Okay, so far we have calculated the active power and we have calculated reactive power. The next step is to find out the reactive power that is supplied to the bank of capacitors, because here it says that the three-phase bank of capacitor is connected in star across the load. So we have to find out what is the reactive power that is being supplied to the capacitor bank. We have two values of kVAR now. We have the value 600, which is being supplied by the cable, and then we have the value of 435.88 after this resistive load is connected. So the amount of reactive power that is sent to the three-phase bank of capacitors would be the difference of both of this. Difference is just subtraction. So just write this here. The reactive power Q supplied to the capacitor bank is equal to 600 minus, we found the value to be 435.889. Now if we subtract the 2, we get 164.11 kVAR. Okay, so this is the reactive power that is being supplied to the capacitor bank. Now the question talks about per phase. Everything seems to be in per phase. So the next point is to find out what is the reactive power per phase. This is the total reactive power, mind you. So next is reactive power per phase would be 164.11 divided by 3. We divide by 3 because it is three-phase. It's a three-phase capacitor bank. So we have 54.7 kVAR. The next step is to find out the voltage, because the question gives us the line voltage. Given the line voltage is 3.3 kV, we need to find out what is the phase voltage, because everything is in terms of phase. So we have phase voltage, formula being line voltage divided by root 3. Please keep this in mind. This is for star connected, which would be, VL is given as 3.3. 3.3 divided by root 3. Let me just get the calculator there. That gives us 1.9052 kilovolts. Now because the line voltage is given to us as 3.3, the units will remain the same. So we have 1.9 kilovolts. Yeah. So the next step is to find out XC. We have to find out what XC is. Capacitive reactance. Consider the basic formula for power. Now we know that power in terms of voltage and resistance is V square by R, right? So if we were to use the terms that we have in this situation, we have the reactive power per phase. So the power would be reactive power per phase. Voltage is phase voltage square divided by R, but in this case XC. Okay, so I hope you see how we get this equation here. If we rearrange the equation in order to find out what XC is, we get XC is equal to V phase square divided by Q phase. So let's evaluate. XC is equal to V phase, we have found it to be 1.905. Okay, now here it is very important to expand. So into 10 power 3 whole square divided by Q phase is supposed to be 554.7 into 10 power 3 because it is kilo. Okay, so if you solve this, please give me a couple of seconds here, we would get 66.36 ohms. This is capacitive reactance. So it is in ohms. The units are in ohms. Now finally we find the capacitance. C is equal to 1 by 2 pi f x c. which is 1 divided by 2, 3.14, 50, 66.36, and the result will give us, the question says that we need to write it in terms of microfarad, so we get 47.96 into 10 power minus 6 farad, and that is 47.96 microfarad. So the final answer here is 47.96. 47.96. Well, I hope this has helped.